previous class, we got ourselves briefly introduced to a pair of charges equal in magnitude, opposite in sign, separated by a very small distance, right? If you recall, we explored two charges, minus q plus q, separated by distance a, which was small compared to distances of this arrangement, points in the surroundings, much smaller than a when measured from this configuration. And what we saw was, okay, first of all, we defined an entity which was, let me call it D because that might have been the terminology I have used, and this vector from the negative charge to the positive charge was the vector D. And we defined the dipole moment of this arrangement as Q into D. Right? That's how we defined the dipole arrangement, the dipole moment of this arrangement. And so if this was the dipole moment vector P, if this was the dipole moment vector P, then all of the points in the surroundings were completely characterized with the help of two numbers r and theta. Any point in the surroundings could be located with respect to the dipole moment vector with a r and theta, right? Different r theta combinations would locate different points in the surroundings, and we assume that this r was always much smaller compared to was much larger compared to D. That means D was much smaller compared to R. Only such points were investigated. Only such points were investigated for the surroundings, right? And if this was a point A, then the potential at this point A corresponding to R and theta turned out to be, if you remember, Kp cos theta by R squared. And if this vector was R, then this potential in vector notation turned out to be K P dot R by R cubed, right? K P dot R by R cubed. And this arrangement produced an electric field at A in the radial direction, an electric field in the tangential direction, right? There was an electric field produced in the radial direction, ER, that was 2 Kp cos theta by R cube. That was the component of the radial field in the component of the electric field in the radial direction. And then there was a tangential component, E theta, which was Kp sin theta by R cube. These were the things that we obtained with some basic computations, right? Dipole moment placed in an electric field. Dipole moment placed in a non-uniform electric field. See, if a dipole was placed in a uniform electric field, this is a dipole. And if it was placed in a uniform electric field, then plus q and minus q will experience forces equal in magnitude, opposite in direction, and there would be no net force. There would be no net force, right? But if it's, suppose this is placed along the x-axis. Suppose this is placed along the x-axis. Minus q is at x, plus q is at x plus dx, small separation, right? And it's placed in an electric field E, which is varying with x, E as a function of x, electric field varying with x. Now this would be, let's say, if E is the electric field here, if E is the electric field at x, then this is a negative charge. A negative charge will experience a force opposite to the direction of the electric field. A positive charge will experience a force in the direction of the electric field, but a negative charge will experience a force opposite to the direction of the electric field. So this minus q will experience a force q E at x? Yes or no? Yes or no? What is the problem? Okay, think about it. Minus q into Ex is the force that it experiences in this direction. So minus q into Ex in this direction is like q into Ex in this direction. I was avoiding to say all that. I thought it is just common sense that, you know, q is the magnitude of the charge, so magnitude of the force is q Ex, right? Right? And what about this? This experiences a force q E at x plus dx. Yes or no? So what's the net force on the dipole? Q into E at x plus dx minus E at x. That's the net force on the dipole. Right? Force on this minus force on this. That's the net force on the dipole. Yes or no? Yes. Right? Now, this is like change in E. Change in E over dx. This is change in E over dx. Right? So this is like Q into change in E. Change in E. Final value of E minus initial value of E. Yes or no? Change in E. This could also be written as Q into dE dx into dx. Yes or no? Now, this is like Q into dx into dE dx. How about it? Hey, Q is the magnitude of charge held by each of the two members of the dipole, and dx is the separation between them. So Q into dx is what? The dipole moment of this arrangement. Q into dx is the dipole moment of this arrangement. So this is like P dE dx. P dE dx. That's a force experienced by a dipole when exposed to a variable electric field. If the electric field is constant, dE dx will be 0. The force experience will be 0 very clearly. Yes or no? If E is constant, dE dx would have been 0 and the force experience would have been 0 evidently. Right? Say, for example, let me explain to you what I mean by this. So this is an important result. Force on a dipole in the direction of an electric field. In the x direction, dipole kept aligned with the electric field. The dipole kept aligned with the electric field. The force on that dipole is going to be P into dE dx, where P is the dipole moment of the arrangement and dE dx is about the electric field, how the electric field is varying along the dipole moment, right? Can I wipe this off? Suppose there is a charge uniformly distributed on a ring. Of radius r, centered at O, charge Q uniformly distributed on this ring. Right? Now let me say that the axis of the ring is the x-axis. Let me say that the axis of the ring is the x-axis. Then, very clearly, if the dipole is placed at x, there will be electric field at x given by Ex. What's the electric field at x from O? This distances are measured from O. The origin, this is my x-axis. So this distance is x measured along the axis. So what's the electric field? E at x, K Qx by r squared plus x squared to power 3 by 2. That's the electric field at x, right? It's varying in the x direction. Now, if you happen to place a dipole P, aligned with the electric field in the x direction, aligned with the electric field in the x direction. Then what would be the force experienced by this dipole? The force experienced by this dipole placed at x, force experienced by the dipole placed at x is going to be P dE dx. P dE dx, that's going to be the force experienced by the dipole. So which is like P d dx of the electric field, which is kqx by r squared plus x squared to power 3 by 2. Yes or no? That's a force experience. So you can differentiate this with respect to x and obtain the magnitude of the force experienced by the dipole placed on the axis of this ring at a distance x from the center of the ring. Right? Now if you recall, the variation of the electric field with x along the axis of the ring was like this. Initially linear, and then it reached at x equal to r by root 2, it reached a maximum. Remember that? So that is on one side of the ring, and on the other side of the ring, it's only the direction of the electric field that will vary. So this is x equal to minus r by root 2. Remember this? Now, do you realize that at x equal to r by root 2, dE dx is 0? At x equal to r by root 2, dE dx is 0. Slope of the E versus x graph is 0, right? At x equal to r by root 2, dE dx is 0. That means, if you happen to place this dipole at x equal to r by root 2, then the dE dx, that means differentiate this with respect to x and put at x equal to r by root 2, this will turn out to be 0. So if you happen to place the dipole at x equal to r by root 2, then this dE dx will be 0 for x equal to r by root 2. The force experienced by the dipole is going to be 0. Yes or no? Now, sometimes we could reduce certain systems to combination of dipoles. It may not be like one dipole, but it could be like multiple dipoles. You can play intelligently and reduce a system of charges separated by short distances to an equivalent collection of dipoles. Let me show you. But you understand all of this, right? Not a problem, no? Say for example, suppose there is a charge minus 2q placed at a point. And there is another charge q separated by a very short distance d from this charge, and another charge q separated by a very short distance d from this charge, right? And this angle say is theta. This angle say is theta. Now if these d's are very small, I could reduce this electrical arrangement to two dipoles, a combination of dipoles. How? What I could do is, I could think about this as this minus 2q I can write as minus q and minus q, right? So there is one minus q and there is one q. This will be one dipole. There is another minus q and another plus q. This would be another dipole. So these are essentially two dipoles. Do you see that? Do you see there are two dipoles? Right? One minus q with this q would be one dipole. Another minus q with this q would be the second dipole. These are the two dipoles. Right? And The first dipole would be of magnitude P equal to Q into D. The other dipole would also be of magnitude P equal to Q into D. These are the two dipoles. Yes or no? Now if somebody says what's the net dipole moment of this arrangement? A resultant of these two vectors QD including an angle theta. The net dipole moment of this arrangement, would be the resultant of these two vectors. One vector P, which is one dipole moment, another vector P, another dipole moment, right? Resultant of these two vectors. Very clearly, since these vectors are equal in magnitude, their resultant would be equally inclined to the two. So this angle will be theta by 2, this angle will be theta by 2. And each of the p's could be resolved as p cos theta by 2, p sin theta by 2. So the two horizontal components add up to 2p cos theta by 2. The two components in this direction, they are like p sin theta by 2, p sin theta by 2. Yes or no? These are the vertical components of the dipole moment vectors, and they cancel off. So what's the net dipole moment of this arrangement? 2p cos theta by 2. This would be the net dipole moment of this arrangement. This would be the net dipole moment of this arrangement. Got me? Sounds good? Suppose I had, tell me if you're done. This and this. This and this. All that I have done is I have written minus 2q as 1 minus q and 1 minus q. 1 minus q, I got it married to this plus q. The other minus q, I got it married to this q. So this minus q and this q produced one dipole. This minus q and this plus q produced another dipole, both having the same dipole moment magnitude qd at an angle theta included between them. So the resultant of these two vectors p and p would be equally inclined to the two p's, right? And you resolve them. P cos theta by 2 plus p cos theta by 2, p sin theta by 2, p sin theta by 2 will get cancelled. The net would be 2p cos theta by 2, right? Again, let me give you another example. Say this is the x-axis, this is the y-axis. There is, say, minus 2q here. There is this plus q here. This is a units. There is another plus q here. This is also a units, right? A is very small. A is a really small number, say, okay? And I want to find the potential at a point A whose coordinates are 4, 3. Say I want to find the potential at a point A whose coordinates are 4, 3. Now, first of all, like before, this minus 2q could be written as minus q and minus q. This minus q and this plus q would be one dipole, and this minus q and this plus q would be another dipole, right? So the first dipole moment vector p1 would be like q into a into I cap. Yes or no? That's the direction of this dipole. This dipole moment has magnitude q into a and is along the positive x direction from the negative to the positive charge. And then there is a dipole moment vector p2, which is like another minus q plus q. This dipole moment is like q into a, but j cap. Yes or no? Right? And the net dipole moment of this arrangement is going to be p1 plus p2 is going to be the net dipole moment of this arrangement. That's going to be the net dipole moment of this arrangement. This is going to behave like a dipole moment p, which is p1 plus P2, which is going to be adding the two, QA into I cap plus J cap. Yes or no? So then, so this is my net dipole moment P, right? This is my net dipole moment P. What's the position of this point A with respect to this? This R is what? 4I cap plus 3J cap. That's the position vector of this point with respect to the dipole, right? So the potential at A is going to be K times P dot R by R cube. Potential at A is going to be P dot R by R cube, K into P dot R by R cube. That's going to be the potential at A, which is like K into P, which is QA into I plus J. Dot the position vector of the point A with respect to the dipole, which is 4I cap plus 3J cap, divided by R. Hey, this length is 5 units, root 4 square plus 3 square, right? This is 5 units, so this R in magnitude is 5, so divided by R cubed, which is 5 cubed. That's going to be, now you can find the dot product. So 4 plus 3, 7. It will become 4 plus 3, 7. So this becomes like a 7 KQA divided by 125. This would be the potential at the point A. Is the idea clear or not? So there are occasions, it's not like every system could be reduced to combination of dipoles, but sometimes we can. Sometimes we can. And the only situation where it makes sense to reduce it to a dipole arrangement is if the separation between the charges is really small compared to the point, say, that we are looking in the surroundings. That's when it makes sense. Because after all, to do those calculations, we have made that approximation, that this distance is really small compared to distances in the surroundings. So it makes sense when I investigate points A in the surroundings that are much further compared to this distance A. Because this formula would be true only under those conditions. This formula would be true only under those conditions. Clear? Clear, no? Oh, okay. Okay. Wipe it off? Suppose I have a semicircular ring. This is a semicircular ring of radius r with charge q uniformly distributed on the circumference. With charge q uniformly distributed on the circumference. Okay? Center of the string. Right, there is plus q here and on this ring, and there is a minus q kept at O. There is a minus q kept at O. There is a minus q kept at O. Now, this minus q is like infinity of these minus dq's, minus dq, minus dq, yes or no? And this plus q is like infinity of these plus dq's, plus dq, etc., yes or no? So which means each minus dq here can be paired with, each minus dq here can be paired with a plus dq to produce a dipole? To produce a dipole? Yes or no? We have infinity of dipoles here. We have infinity of dipoles. I want to find the net dipole moment of all those dipoles. You know what I'm saying? So what I do is, I, at an angle theta, I take a small portion of the ring. At an angle theta, I take a small portion of the ring which subtends an angle d theta, at the center. And this houses a charge dq, this houses a charge dq. Now, there is a plus dq here which sources itself with another minus dq here, and this minus dq and plus dq will constitute a dipole, right? And that dipole moment would be like this. That dipole moment would be like this. dp, that dipole moment would be like a dp like this. The minus dq here, look, I look at a plus dq here and a minus dq here, right? This is the point. And this minus dq and this plus dq, this is the plus dq, together will produce a dipole moment vector dp, will produce a dipole moment dp. And if this angle is theta, then this dp will also make an angle theta with the horizontal. This dp will make an angle theta with the horizontal, right? Clear? Now, what is this dp? This dp is very clearly dq into a, into the radius. dq into the radius is the dipole moment dp, right? Yes or no? Clear? And what is this dq? dq is the charge over a length r d theta. Yes or no? dq is charge over a length r d theta. Yes or no? This length is r d theta. Yes or no? Almost like a point charge. R d theta, right? Now, what is the charge per unit length over the circumference? Lambda, which is q by pi r, charge per unit length. Charge per unit length on the circumference of the ring is charge divided by the circumference, pi r, right? That's, so what's the charge on this? The length of this, r d theta into lambda, charge per unit length into r d theta. That's a charge on this dq, you know, charge per unit length into the length. That's a charge on this dq, right? Which is q by pi r into r d theta. Q means, let's say capital Q in this case. Capital Q is the total charge. So Q, capital Q is the total charge. Or have I said Q? Okay, let me call it small q only. Let me stick to small q. That's all right. Q by pi r, r d theta. Q is the total charge distributed on this. All right. So this gets cancelled. So this becomes like a q by pi into d theta. Right? So now this dq I can write as q by pi r into d theta. This replacing dq by q by pi d theta. That's a dipole moment dp. Now the important thing is, various minus dq's will produce dp's in different directions. Yes or no? So you can't add these dp's like you add scalars. You can't add these dp's like you add scalars. But the interesting thing is that with every dp here, you'll be able to find another dp whose horizontal component will cancel each other. Yes or no? If there is a dp produced by this combination, there is going to be a dp produced by this combination, and their horizontal components will cancel each other. So the net dipole moment parallel to the diameter is going to be 0, isn't it? If this angle is theta, this is also theta. That means all the dp cos thetas will add up to 0. Yes or no? That means integral dp cos theta, where theta runs from 0 to pi, has to be 0 because of this pairwise cancellation. Yes or no? Pretty easy to see that, right? That means the net dipole moment would be sum of all the dp sine thetas, right? This is theta. So all that we need to do is we need to add up all the dp sine thetas which are perpendicular to the diameter. Dp sine thetas are all perpendicular to the diameter, yes or no? So all that we need to do is sum up all the dp sine thetas, sum up all the dp sine thetas, right? So the net dipole moment would be sum of all the dp sine thetas, where theta runs from 0 to pi. Sum of all the dp sine thetas, where theta runs from 0 to pi. Right? All the dp sine thetas are in the same direction, so we can add them like scalars, right? So which is like integral 0 to pi dp, which is qr by pi sine theta d theta. Right? If you integrate sine theta, you get minus cos theta. If you supply the limit 0 to pi, you will get 2. If you integrate sine theta, you get minus cos theta, you will get 2. If you supply the limits, you will get 2. Cos pi is minus 1, cos 0 is plus 1. You will get 2 as a difference. You can check that. I am not cheating you. So, the net dipole moment of this arrangement, which is in this direction, purely in the vertical direction, turns out to be 2qr by pi. 2qr by pi. Yes or no? Which is like q into 2r by pi. Isn't it? Which is q into 2r by pi. Now, hey, what turns out should not be applied. Now, I'll tell you, one would be tempted to believe the following after seeing this result. Do you remember, if this is a uniform circular ring, semicircular ring of radius r, the center of mass of this is at 2r by pi? Is that 2r by pi? Recall this result? No. The center of mass of this arrangement is like 2r by pi. Now, it's as if now this entire plus q could be imagined to be at 2r by pi here. Then there is a minus q here and there is a plus q here, and that minus q and plus q separated by 2r by pi is q into 2r by pi. But don't use this result in this form in any other situation, it will fail. Okay, in this case it happens. I'll leave you to evaluate why this happens here, and may not always happen, but in this case it's as if I can replace this entire charge plus q in the circumference by a plus q at the center of mass of the ring, which is at 2r by pi. So it's now like a minus q that originally was, and this entire plus q to be here, so that the dipole moment of this arrangement is going to be q into 2r by pi, and would be in this direction, from minus to positive. Do you know what I'm saying? So now for this arrangement in the surroundings, you want to find potentials and electric field because of this arrangement, right? And if this radius is really, really small, right, and you want to find potentials, then what would you take recourse to? If you didn't reduce it to a dipole moment, then for all this entire charge distribution, you will find the potential at a point. Because of this minus q, you will find the potential and you will add them up, right? Right? Instead, it could be reduced to an equivalent electrical dipole. So now we have results ready-made for an electrical dipole, which could be readily used. This is on the premise, obviously, that the radius r is really small compared to what we are measuring in the surroundings, right? So it simplifies your computation largely. Otherwise, see, to find the potential at this point for this arrangement asymmetrically located could be quite a challenge. May not be that easy always. Shall we proceed? Now, force between a charge and a dipole. So a point charge and a dipole. We found the force on a dipole when placed in a non-uniform electric field, right? Now let me illustrate a couple of situations where there is a point charge and there is a dipole, right? I want to find the force that that point charge will exert on the dipole. I want to find the force that the point charge will exert on the dipole. Say for example, so force exerted by a point charge Q on a dipole, for example. Say this was my, I'll take only special cases. There is a dipole moment P, right? And at a distance small r from this dipole, say I've kept a charge plus q. At a distance small r from this dipole, I've kept a charge plus q. I want to find the force that this charge q exerts on the dipole. Now, instead of doing that, finding the force that the charge exerts on the dipole, let's find the force that the dipole exerts on the charge. Then from Newton's third law, those forces would be equal in magnitude and oppositely directed. So instead of finding the force on the dipole, let me find the force on the charge q because of the electric field of the dipole, right? Now, see, for this point q, for example, this point where plus q is located, theta will be pi for such a point, yes or no? Do you realize that if q was here, then theta would be pi? Theta would be pi, and if theta is pi, E theta would be 0, right? E theta at this point plus q would be 0. Yes or no? Because theta is pi, sine pi is 0. This is my radial direction, ER. Theta is pi means put theta equal to pi, it turns out to be minus 2kp by r cubed, right? So electric field in the radial direction is minus 2kp by r cube, minus 2kp by r cube. Yes or no? That means if it is minus 2kp by r cube leftwards, it is like saying it's 2kp by r cubed rightwards. Minus 2kp by r cube leftwards is the same as saying plus 2kp by r cubed rightwards. Yes or no? Is that okay to do? Right? So this is like saying there is a dipole P and the electric field here is in this direction, which is 2kp by r cubed. That's a net electric field because E theta is 0. Because E theta is 0. Theta being pi. Yes or no? That means this charge q will experience a rightward force. This charge q will experience a rightward force. How much is it? Q into the electric field, right? Force experienced by this charge q is going to be rightwards, which is q into E, which is 2kqp p by r cube. Yes or no? So the dipole exerts on this charge Fq to the right. The charge will exert on the dipole Fq to the left. Yes or no? Newton's third law. The dipole exerts on this charge Fq to the right. Therefore, the dipole exerts on the charge Fq to the right? So, the charge will exert on the dipole Fq to the left. Newton's third law. So, on the dipole, a force Fq is going to be acting to the left. Why? Because the force on the charge is Fq to the right. They will constitute an action-reaction pair. They will constitute an action-reaction pair. Yes or no? Suppose, let me place the charge somewhere else. I'm deliberately choosing simpler positions because they ease out computations. But just to illustrate what you might want to do in general. Can I wipe this off? Say, this is a dipole P and a charge plus Q is kept here. Now this plus Q is about theta equal to 90 degrees. Yes or no? Now if theta is 90 degrees, ER will be 0. ER will be 0 and E theta would be Kp by R cubed. Right? So ER, which is this length is R. ER is going to be 0. Theta is 90 degrees and this, all that you will witness is E theta, which is going to be Kp sine 90 degrees, which is 1. Kp sine 90 degrees, which is 1 by R cube. Yes or no? So then, the force on this charge would be simply Q into E theta, right? So force on the charge is Fq to the left. Force on the charge is Fq to the left. What is Fq? Fq is Q into E theta. That's the force that the dipole exerts on the charge. So the force that the charge will exert on the dipole would be Fq to the right. Would be Fq to the right. That's the force on this type. Yes or no? Let me see the force that one dipole exerts on another dipole. Let us compute the force that one dipole exerts on another dipole. Are you confused or are you all there with me on this? No confusion, na? Say there is a dipole moment P1, there is a dipole P1 directed as shown at A, and there is another dipole P2. And let's say they are separated by R. So, what I do is, I'll compute the force on P2, the dipole P2, because of the electric field produced by, because of the electric field produced by P1, because of the electric field produced by P1. Now, if you look at P1, then what's theta at B? 0. Right? I'm computing my electric field because of P1. Then the point B, as far as P1 is concerned, theta will be 0. If theta is 0, then E theta will be 0. That means E theta is like this. E theta is 0. And ER is 2 kp by r cube because theta is 0. 2 kp by r, right? ER is 2 kp by r cube. Hmm? Now, so this is a dipole placed in this electric field. Yes or no? Hmm? This is the electric field because E theta is 0. So now I have a dipole P2 which is placed in an electric field. This is at a distance r from P1. This is a dipole placed in an electric field ER, which is 2 kp by r cubed. Yes or no? The force on a dipole placed in an electric field would be P2 into dE dr. Instead of x, you have r. Yes or no? Force on a dipole, I derive that result, P dE dx. Right? So in this dipole, the force is going to be P2 into dE dr. Yes or no? Force on dipole P2, F2, is going to be P2, which is its dipole moment, into the electric field dE dr to which it is exposed. That's the force on this dipole P2. Right, it's aligned in the r direction. The electric field is varying only in the r direction. So this is like P2 dE dr. This would be minus 6k P1. This is P1 by the way. Minus 6k P1 by r to power 4. If I differentiate this with respect to r, I'll get minus 6k P1 by r to power 4. Right? R to power 4. Negative means the force on this dipole is leftwards. It's negative. It's turning out to be negative. That means the net force on this dipole P2 must be leftwards. This is what it means. And of magnitude 6k P1 P2 by r to power 4. The magnitude of the force is 6k P1 P2 by r to power 4 and is leftwards on P2. And therefore on P1 it's the same magnitude but rightwards. Yes or no? Attractive force. There is net attractive force between the two dipoles. Got me? And you can figure out other combinations as a fun exercise. You could have had a dipole P1 here and a dipole P2 here and work out this situation. It's not going to be difficult. It's not going to be difficult. It's the same idea that would have to be used. Right? Can I wipe this off? I'll wait. The magnitude of the force on dipole P2 is 6k P1 P2 by r to power 4. Since it's negative, it's leftwards. So force on P2 is leftwards and is of magnitude 6k P1 P2 by r to power 4. The force on A is going to be rightwards and of the same magnitude. Okay? Got me, now? Wipe it off? Good. Now, the next thing that I'm going to explore is the torque acting on a dipole when exposed to a uniform electric field. Torque on a dipole when exposed to a uniform electric field. Right? There is a charge minus q here, there is a charge plus q there. This is a dipole. And say the two are separated by a distance d. Two are separated by a distance d. And the whole arrangement is placed in an electric field, say parallel to this line, making an angle theta. This electric field E is like this, making an angle theta with the dipole moment, right? This is the dipole moment. Minus q to plus q is the dipole moment and is of magnitude q into d, directed from the negative to the positive charge. That's the dipole moment of this arrangement. Now, this charge q will experience a force in the direction of the electric field, q into E. This charge minus q will experience an equal and opposite force opposite to the direction of the electric field, obviously, q into E in this direction. Yes or no? Negative charges will always experience forces opposite to the direction of the electric field. Now, E makes an angle theta with the dipole moment vector. This is the dipole moment vector, and the vector E makes an angle theta with the dipole moment vector. Okay? Now, realize that this force QE by this charge could be resolved. Now, this is theta, corresponding angles theta. Right now, this QE could be resolved as QE cos theta along the dipole moment and QE sin theta perpendicular to the dipole moment. Yes or no? Right? Now, this QE, like before, could be resolved as, in this direction, QE cos theta, and in this direction as QE sin theta. Yes or no? QE cos theta and QE sin theta. This, right? This angle is theta, vertically opposite angles, theta. So this QE cos theta like this, aligned with the dipole, and QE sin theta perpendicular to the dipole. Yes or no? Now, QE cos theta will get cancelled. They will produce no torque. See, if there is a rod, alright, if there is a force F like this and there is a force F like this, will it produce any torque on the rod? No. These two forces will not produce any torque on the rod, right? It will only cause deformation on the rod. It will not produce a torque on the rod. But if there is a force F like this and there is a force F like this, then these two forces constitute a couple. They constitute a couple. And the torque produced by this combination, which is called the torque of the couple, is F into L, isn't it? These two forces perpendicular to the rod produce a torque. They constitute a couple. You know what a couple is, right? And the torque produced by a couple is magnitude of each of the two forces, either of the two forces, into the distance L between them. That's a torque produced by a couple. So, look at this situation. QE cos theta are like these two forces, longitudinal forces. They produce no torque on the arrangement. But QE sin theta and QE sin theta, they constitute a couple. Yes or no? And the torque of this couple is like QE sin theta into D. That's the torque of the separation between them is D. So the torque of this couple is like a QE sin theta into D. QE sine theta into D is the torque of this couple. But what is Q into D? The dipole moment. Q into D is the dipole moment. P. So that's like a PE sine theta. No, confused? Q into D replaced by the dipole moment of this arrangement into E sine theta. So PE sine theta. Yes or no? So which means now, can I remove this portion? Just this portion? Look, the P is like this. P is like this, the dipole moment vector from the negative to the positive charge. The electric field is like this. And the angle between the electric field and the dipole moment vector is theta. Yes or no? Do you realize this is P cross E? PE sine theta is like a P cross E. And see, P is like this, E is like this. P cross E is into the plane of the board, clockwise torque. Do you see that? P cross E is into the plane of the board. And this QE sine theta also produce a clockwise torque. Clockwise torque. And P cross E is also clockwise. Right? And the magnitude of P cross E is P sine theta. So then can I say that the torque on this arrangement is P cross E? Both the direction and magnitude match. So when a dipole P is placed in a uniform electric field E, it will experience a torque P cross E. Very commonly used result. Very commonly used result. Torque experienced by a dipole when placed in an electric field that is uniform. Dipole moment vector cross the electric field vector. Dipole moment vector cross the electric field vector. Can I wipe this off? Now, a general remark before I proceed with the next very important result on dipoles. Hey, suppose that there is a particle and a force F acts tangentially on the particle, right? The radius of this circle is R. What's the torque of this force about O? F into R. F into R. That's the torque of this force, right? Now, if there is a small change in angle d theta, then this force that was tangential here is also tangential here. This force is practically the same along the tangent at this point. Then, what's the work? What's the displacement? This length? This length is the displacement. R d theta is the displacement. Right? What is the work done by this force? The work done by this force is like F into R d theta. F into R d theta is the work done by this force. R d theta is also almost tangential and F is also almost tangential. So the work done by this force is F into R d theta. But F into R is the torque acting on the particle. Right? So that's like tau d theta. Right? So if you know the torque on a system, important thing, the outcome is that if the torque tau is known and that torque tau results in an angular displacement d theta, then this is called the work done by a torque. This is called the work done by a torque. Work done by a torque. Eventually it was work done by the force F, but it is commonly used to say work done by a torque because this force translates into a torque. So this is the work done by a torque, tau d theta. Work done by a torque is tau d theta. The power associated with this is dw dt. That's a power associated with it. Differentiate this with respect to time. That is tau d theta dt. But d theta dt is omega. D theta dt is omega. Yes or no? Huh? So this is like tau omega. Right? That's a power associated with a torque. Now, so important thing is, if you have knowledge of the torque acting on a system, then, and if it results in an angular displacement d theta, then the work done by the torque is going to be tau into d theta. Now, one thing important, in this case, realize that the torque is clockwise and d theta is also clockwise. Both tau and d theta are in the same sense, both clockwise in this case, yes or no? Both torque and d theta are in the same sense. D theta was like this, clockwise, and torque was also like this. Then the work done was tau d. However, if the torque is like this and d theta is oppositely directed, then the work done by this torque would be minus tau d theta. If torque is in one sense but angular displacement is in the opposite sense, then the work done by this torque is going to be minus tau d theta, is going to be minus tau d theta. That's the work done by a torque in which the angular displacement is in a sense opposite to the sense of the torque. Yes or no? Just like the force. If force and displacement are in the same sense, F into S. But if they are in opposite directions, minus F into S. Same way. Right? Adapted from similar considerations. Is that okay or not okay? Clear, huh? Now, can I wipe this off? So now, if a dipole is placed in an electric field, I'm assuming uniform electric field, there is potential energy associated with the dipole. There is potential energy associated with the dipole, right? Dipole is also effectively a collection of charges, right? So to place those charges minus q plus q in an arrangement in the electric field would require you to do some work, right? And that would be the potential energy of the dipole. That will be the potential energy of the dipole. Let's compute the potential energy of a dipole arrangement when placed in a uniform electric field. Potential energy of a dipole when placed in a uniform electric field. I've already computed the torque experienced by a dipole when placed in a uniform electric field, P cross E. Now the potential energy of a dipole when placed in a uniform electric field. Clear? I hope this is not confusing. You understand why it's plus tau d theta and why this is minus tau d theta? Work done by a torque if torque and angular displacements are in the same sense, this. And in opposite sense, this. Clear? Now, so we, like before, we look at a dipole moment, a dipole minus q plus q, that's a dipole arrangement. Same dipole moment q into d, this separation is d as always, and this is the electric field vector making an angle theta with the dipole. Dipole was P like this, right? The dipole vector P makes an angle theta with the electric field vector, uniform electric field vector. Now, we have knowledge of the torque acting on this. We've seen from the previous situation that torque acting on this is clockwise, and is of magnitude PE sine theta. For the given figure, it is clockwise. Now, what I want to do is, this is a rod holding these two charges minus q and plus q. I cause this arrangement to have an angular displacement d theta anti-clockwise. This arrangement now is angularly displaced by an amount d theta anti-clockwise. You know what I'm saying? Torque tau is clockwise and d theta is anti-clockwise. This is clockwise, and for the figure that I've shown, d theta is anti-clockwise. There is no loss of generality in doing this or the other, so it's just to be more specific. This is a torque because of what? Because of the electric field. This is the torque because of the electric field. Now, if this is rotated very slowly by an amount d theta anti-clockwise, there is some work done by the electric field. Work done by the electric field to which this dipole is exposed. Work done by the electric field to which this dipole is exposed is the work done by the torque because of the electric field. Work done by the electric field means what? What is doing work? The torque of the electric field. That means the work done by the electric field to which this dipole is exposed is the work done by this torque. I'm saying work done by the electric field means work done by the forces of the field. But those forces of the field have translated into a torque. So either I use the forces to compute the torque, to compute the work done, or I use the torque to compute the work done. That's going to be the same. It does not matter. I could have used the forces because of the electric field to compute the work done, right, for this anti-clockwise angular displacement d theta, or I could have, in a simpler sense, used the torque of the electric field. Torque because of the electric field to compute the work done by the electric field. It does not matter. It's going to be the same thing. This is convenient. That's all. Work done by the electric field on this arrangement is going to be the work done by this torque, because this torque is created by the electric field. So if you compute the work done by this torque, you've computed the work done by the electric field, yes or no? So the work done by the electric field is all that I'm talking, right? So the work done by the electric field. This line is, of course, theta equal to 0. The direction of the electric field is theta equal to 0. 0 angle. Work done by the electric field is going to be the work done by the torque. Now realize, torque is clockwise, whereas d theta is anti-clockwise. So the work done by this torque would be minus tau d theta. Work done by this torque is going to be minus tau d theta, because they are in opposite directions. Because they are in opposite directions. Opposite senses, I shouldn't say direction, opposite senses, clockwise and anti-clockwise. Right? Which is like tau, which is Pe sine theta at this instant. It's a variable torque. It's not a constant torque. Torque is a function of theta. So it's a variable torque. Right? So this is like, replace this tau by Pe sine theta. So this is like minus Pe sine theta d theta. Yes or no? That's the work done by the electric field. Hey, work done by the forces of the field will always be negative of the change in potential energy. Yes or no? Work done by the forces of the field will represent what? Negative of the change in potential energy, always. Work done by the external agent would be change in potential energy plus change in kinetic energy. But work done by the electric field unconditionally would be negative of the change in potential energy. Right? So this is the work done by the electric field on this arrangement of dipoles, right? So that must be negative of the change in potential energy of this arrangement. Work done by the electric field on an arrangement results in change in potential energy, and it's going to be negative of the change in potential energy. Yes or no? That's how potential energy was essentially defined. Work done by the forces of a conservative field will be negative of the change in potential energy. That was the definition of the potential energy in a conservative field. What? So this is okay, no? Now, what was my objective? My objective was to compute the potential of this arrangement at theta. Potential energy of this arrangement at theta when placed in a uniform electric field E. Right? what I do is, this was the zero angle line, the direction of the electric field, right? The dipole would have occupied this state sometime. This is plus q minus q. In this case, theta is 90 degrees. In this case, theta is 90 degrees. U will be a function of theta. U will be a function of theta. What we do is, and it does not matter though, for a dipole, we select the zero of potential energy as theta equal to pi by 2. The potential energy at theta equal to pi by 2, we select that as the zero of potential energy. Realize that you can select any configuration as the zero of potential energy. It might change the potential energy from point to point, but the difference in potential energy will be preserved irrespective of what you have chosen as the reference point for defining zero of potential energy. So it is customary, and there are no rules to do this, but what physicists have done is they said, all right, this theta equal to pi by 2, when this arrangement acquires theta equal to pi by 2 perpendicular to the electric field, we will call that as the zero of potential energy of this dipole arrangement. That means u at theta equal to pi by 2 we define to be 0. That's our choice. That's our choice. We choose this to be 0. U at theta equal to pi by 2, we choose to be 0. That's all. Now, let me integrate both sides from theta equal to theta equal to pi by 2, right? So, minus Pe sine theta d theta equal to minus du. Let me integrate both sides from theta equal to theta. When theta is theta, u will be u at theta. When theta is theta, u will be u at theta. When theta is pi by 2, u will be 0 by choice. You know what I've done here? When theta is some theta, u is u at theta. When theta is pi by 2, I have chosen u to be 0. This will give me variation of u with theta if I integrate both sides. Let's do that. The minus in the first place will get cancelled, right? So, yeah. So, in this case, u at, this is 0 minus u, which is 0, minus u at theta, yes or no, the right hand side. I've taken minus out. 0 minus u theta is what I get, right? When I integrate, 0 minus u theta is what I get. The left hand side minus, if I integrate minus sine theta, I get cos theta. If I integrate minus sine theta, I get cos theta. So that's Pe cos theta. Theta runs from theta to pi by 2. Minus sine theta when integrated gives me cos theta. Right now? So Pe coming out, cos theta, theta runs from theta to pi by 2. You know? So this is cos 90, which is 0, minus cos theta. So this is minus Pe cos theta. That's equal to u at theta. Yes or no? This was my dipole moment. This was my electric field E. This was the angle theta. What is Pe cos theta here? P dot E. P dot E. Pe cos theta is going to be P dot E. So, u at theta is going to be minus P dot E. U at theta is going to be minus P dot E. Potential energy at an angle theta would be the dot product of the dipole moment vector and the electric field vector. Negative of this. On the premise that at theta equal to 90 degrees, u was 0. At theta equal to 90 degrees, u was 0. This gives me the potential energy in terms of theta minus P dot E. Clear? Now, if you have finished copying, let me know. All of you? So, so this was my dipole moment P. This was my electric field E. And the angle between the two was theta. The potential energy of this arrangement in magnitude is minus PE cos theta. Minus PE cos theta, right? Do you realize that when theta is pi, u is maximum? It becomes plus PE. When theta is pi, you assume some maximum value, plus PE, right? Maximum potential energy. And when theta is 0, u is minus PE. When theta is 0, which is u minimum. At theta equal to 0, potential energy acquires the minimum value. At theta equal to pi, it acquires the maximum value. Yes or no? When theta is pi, u becomes u max, which is P into E. When theta is 0, it becomes minus P into E, which is the minimum value of the potential energy. Yes or no? All mechanical systems. If you finish copying this, let me know. All mechanical systems subject to conservative forces have a very special trait. They feel comfortable with lower values of potential energy. They feel uncomfortable with higher values of potential energy. Lower values of potential energy gives them stability. Higher values of potential energies make them unstable. No. Purely physics. Purely physics. Those guys mess it up when they try to use physics and chemistry. That's the only problem. Let me take a little bit of a detour to explain a few things. A general principle of mechanics. Can I wipe this portion off? Just retain that. Essentially, given a choice, systems would want to be in the lowest states of potential energy. That's the reason when you drop a wall, it falls, because it can acquire, it has the potential of acquiring lower potential energies. It feels good in lower potential energy states. When you place a charge in an electric field, positive charge, it moves in the direction of the electric field, along the electric field, because in the direction of the electric field, the potentials decrease, potential energies decrease. It feels good that way. It races up to infinity because that's the zero of potential energy. It's in a zeroth spiritual state. Now, let me think of a particle in a force field in the x direction. Force acting on the particle in the x direction. And its potential energy versus x. Suppose its potential energy versus x say is like this. That's how its potential energy varies in the x direction for a particle, generalized particle. This is generalized mechanics, right? Which we will deploy here. But for the time being, get a hang of this. There is a particle that is placed in a force field along the x-axis, and for different values of x, the potential energy of the particle is like this, right? Again, if you recall from work power energy, the force acting on the particle in the x direction is minus du dx. Yes or no? If du dx is 0, the force is 0 and the particle is in equilibrium. Right? Fx is 0 means du dx is 0, or rather du dx is 0, Fx is 0, the particle will be in equilibrium. Wherever du dx is 0, the particle will be in equilibrium. Wherever du dx is 0, the particle will be in equilibrium. Yes or no? You know? Because force is given by minus du dx. Let's say one-dimensional force field to explain the concept in a simpler manner. Huh? Du dx is what? Du dx represents slope of u versus x graph. Du dx represents slope of u versus x. You know? So, say at x equal to x1 and at x equal to x2. Do you realize the slope at x1 is 0? Slope at x2 is also 0. Du dx is 0. Slope at this point, du dx is 0 at x equal to x2. Du dx is 0 at x equal to x1. At x equal to x1. Right? Because the right? Do you realize that slope of the tangent represents du dx? It's 0 at x equal to x1 and 0 at x equal to x2. That means when the particle was at x equal to x1, the force was 0. When the particle was at x equal to x2, the force was 0. That means at x equal to x1 and x2, the force acting on the particle at x1 is equal to force acting on the particle when it's at x2, each will be 0. The particle is in equilibrium at x1 and x2. Particle is in equilibrium when it's at x equal to x1 and is in equilibrium when it's at x equal to x2. That's the common trait between x1 and x2. But the question is, what is the difference between the two kinds of equilibrium? Both x1 and x2 represent states of equilibrium because the net force because of the field is 0. They represent states of equilibrium of the particle. Right? Now, let us try and understand the difference between this and this. This x1 is where the potential energy is minimum. This x2 is where the potential energy is maximum. And what I am going to establish is that this is a preferred choice. x1 is a preferred choice of equilibrium for a particle. x2 is not a preferred choice of equilibrium for the particle. When the particle is at x1, if you don't do anything to the particle, it will stay there. What I will prove is if you displace the particle slightly to the left or right, it will come back to x1. But when it's at x2, when the particle is at x2 and you displace the particle slightly to the left or right, it will take that gladly and will move away from this state of high potential energy. It does not enjoy that state. All that I'm saying is both are states of equilibrium. This is a state of lowest potential energy. This is a state of highest potential energy, right? Both states of lowest and highest potential energies represent equilibrium states because in both cases du dx is 0. But what I'm saying is for the particle, x1, being at x1 is a preferred state. Because if the particle was at equilibrium at x1 and you displaced it slightly to the left or right, it would come back to x1. I'll show that. But when it's at x2 and you gave it an option of being displaced to the right, it will move away further and further from x2. I'll prove that. I'll prove that. So x equal to x1, which represents a state of lowest potential energy of a particle, is a preferred state. X equal to x2, which is a state of highest potential energy of the particle, is not preferred. We'll see how that happens. But do you understand my assertion? You understand my assertion though, right? So both lowest and highest potential energy states are states of equilibrium. So let's say when the particle is at x equal to x1. When the particle is at x equal to x1. This is my x-axis and the particle is at x equal to x1. And this is its potential energy. This is its potential energy at x equal to x1. Look at the region in the proximity of x equal to x1. This is u versus x. When I displace the particle slightly to the left, when the particle goes from p to p prime, displaced slightly to the left of x1, the force that it experiences would be slightly to the left of x1, the force that when it's moved to this, right, slightly to the left of x1, the force that the particle will experience will be negative of the slope, negative of this slope, yes or no? The slope of this line is du dx. The slope of this line is du dx. The slope of this line is du dx at this x, right? Slightly to the left of x1. The slope of this line is du dx, which you can see is negative. Which you can see is negative. So minus du dx will be positive. To the left of x1, minus du dx will be positive, yes or no? But minus du dx is the force acting on the particle, which is positive. That means when the particle is displaced to x, to the left of x1, then it experiences a rightward force, which is a restoring force, which is trying to bring it to p, which is trying to bring it to p. Right? It wants to be at p. That's why when you displace it slightly to the left, it experiences a force to the right, attempting to bring the particle back to p, because that was a state of very low potential energy of the particle. Right now? Again, displace the particle slightly to the right of x1. Displace the particle slightly to the right of x1 at this x. Now at this x, the du dx will be the slope of this line. At this x, du dx would be the slope of that tangent. Right? And do you see in this case, du dx is positive? The tangent makes an acute angle with the positive direction of the x-axis. Right? So the force acting on the particle, which is minus du dx, will be negative. That means if I displace the particle to p double prime at this x, right, the force experienced is negative. Negative means leftward force. The particle experiences a negative force means leftwards. That means that will bring the particle, that will attempt to bring the particle back to p. So this position, so if you displace the particle slightly to the left of p or to the right of p, it will be brought back to p. It will be brought back to p. P is a state of equilibrium of the particle, but a preferred state of equilibrium. When slightly displaced to the left of p or slightly displaced to the right of p, the particle will be brought back to p. Particle would choose to come back to p. It's a state of not just equilibrium, but it's called stable equilibrium. It's called stable equilibrium. This state at x equal to x1 is a position of stable equilibrium. It's a position of stable equilibrium. It's a position of stable equilibrium. In contrast, so a position of least potential energy is a position of stable equilibrium, In contrast, look at x equal to x2. This is also equilibrium. Is it getting very difficult? No, no. Everything? You mean this or this? This one? Okay. So, the particle was at P, which is x equal to x1. How much potential energy did it have? This was the potential energy that it had. What was the force acting on the particle? Minus du dx, which was 0. Right? So, x equal to x1 was a state of equilibrium. Net force acting on the particle was 0 because du dx was 0, so minus du dx will be 0. No confusion on that? Now, when I displace the particle slightly to the left of x1, when it comes to p prime, right? This position, right? Look at the region surrounding x1. Look at the region surrounding x1, right? When you look at the region surrounding x1, this is a point x to the left of x1, right? At this x, what's the force acting on the particle? Minus du dx. But look at du dx. Du dx is negative at this point. Du dx is the slope of the tangent at x, which is negative, as you can see. So if du dx is negative, minus du dx will be positive. So force will be positive. That means when the particle is slightly shifted to the left, it will experience a positive force, which is rightward force, which would want to bring it back to x1. Similarly, you can look at what happens when I shift it slightly to the right of x1. Du dx will be positive. Minus du dx, which is the force, then will be negative. If the force at x is negative, it will bring the particle back to x1. It's stable equilibrium. It is stable equilibrium. So lowest potential energy states are states of stable equilibrium, right? Now look at x equal to x2 then. No confusion, right? Get this concept right. It's important to understand this, right? There isn't a choice. Now, so this was my x direction and the particle was placed at x2. When at x2, du dx was 0, potential energy was maximum, force was 0, particle was in equilibrium at x equal to x2 because du dx was 0 at x equal to x2. Now, when I shift the particle from p to p prime to the left of x2, slightly to the left of x2, at this point. When shifted slightly to the left of x2 at this x, right? This would be its potential energy. At x, what would be the force acting on the particle? Well, this would be my du dx. The slope of this line will be my du dx, right? Positive slope, du dx will be positive, right? And if du dx is positive, the force acting on the particle, which is minus du dx, will be negative. That means when I shifted it to the left, negative force means force acts to the left. Because it's clearly declaring, I don't want to go to x2. If the force acting on the particle is to the left, it's clearly declaring I don't enjoy x equal to x2. I want to move away and away from it. So if you displace it slightly to the left of x2, the particle will go further and further away from it. Similarly, to the right of x2. Same thing. If you displace it slightly to the right of x2, it will keep moving further and further to the right. Again declaring openly, bluntly, plainly, clearly, x2 is not my choice. It's a state of such high potential energy, let only the big guys reside there. I am better off with lower potential energy states. This is a state of equilibrium, but a state of unstable equilibrium. X equal to x2, which gives us high potential energy, highest potential energy, is unstable equilibrium, right? So x equal to x1, which was lowest potential energy, was stable equilibrium. X equal to x2, which was the highest potential energy, was unstable equilibrium. That's the trade-off. That's the trade-off. work hard in life, all your life, to acquire the state of highest potential energy, but unfortunately, alas, you'll be terribly unstable there. Be in the ground state, reside in the well. This is the well of potential energy. Most preferred state, particles like human beings will remain comfortable in those states. Lower potential energy states, which lowest potential energy states, which is not just equilibrium, stable equilibrium is a reflection of human mind also. It's a reflection of modesty. This is reflection of arrogance, high power and pelf. This is modesty. Low potential energy, I'm content. I like the state. Arrogance, high potential energy, don't like the state. Finish. This is how it goes, right? Physics reveals life. All right, so you understand stable and unstable equilibrium. Bottom line is, lower potential energy states preferred, lowest potential energy state, this is the well, stable equilibrium. Highest potential energy, equilibrium, but unstable equilibrium. Right? Now, let's come back to the dipole. Okay? Why I gave you all these stories. But so far so good. Yes, please ask. Huh? That describes life. Life. What? Subject. Now, see, the moment you said subject, I couldn't even think of chemistry because I never even looked at it like a subject. It was abject. You know, for those who are followers of chemistry and try to interpret my statement, there is a thin line between the numerator and denominator. There is a thin line between the numerator and denominator, and only a fraction of people understand this, those who are rational. Okay, let's proceed. So far so good, right? You understand all that I'm saying, including this. So, the potential energy of a dipole when exposed to a uniform electric field is minus Pe cos theta. Theta is the angle between the dipole moment vector and the electric field vector, right? And like I said, theta equal to pi produced maximum potential energy, theta equal to 0 produced lowest potential energy, right? So theta equal to 0 must be stable equilibrium, theta equal to pi must be unstable equilibrium. U versus theta, the graph of U versus theta is as follows. U as a function of theta versus theta, it will be cosinusoidal, like a sinusoid only, cosinusoidal, right? And at theta equal to 0, it's minus Pe, minimum. At theta equal to 0, it's like minus Pe, right? At theta equal to pi by 2, it will become 0 because that's how we had defined it, right? So this is theta equal to 0, and then at theta equal to pi by 2, it becomes 0. It was our choice, not that it became 0, right? And at theta equal to pi, it was maximum, and so on and so forth, right? So theta equal to 0 was stable equilibrium, theta equal to pi was unstable equilibrium, right? Theta equal to 0 is a state of stable equilibrium for the dipole. Theta equal to pi is unstable equilibrium. So, say there are two charges plus q and minus q, and on particles of mass m each. Particles on mass m each. After all, you know, charges will not come without mass. So, right now. And let's say the rod that connects these two charges has also mass m and has length L. The rod that connects these two charges has mass m and length Okay. And the whole thing is placed in an electric field E. The whole thing is placed in an electric field E that makes an angle 30 degrees with the rod as shown. 30 degrees with the rod as shown. So, first of all, like I demonstrated, there is going to be a torque acting on this system. There is going to be a torque acting on this system, right? The torque acting on this system is going to be PE sine theta. That's a clockwise torque, right? That is sine 30 degrees, that is PE by 2, that's a torque, right? Very clearly, this is the center of mass of the system. What will happen to the center of mass of the system? Nothing. The whole system starts from rest. The net force on this system is 0 because QE and QE like this, net force is 0. That means the acceleration of the center of mass is 0 because the net force will reflect itself on the center of mass. Acceleration of center of mass is 0. Center of mass was at rest and remains at rest, right? So the whole thing will revolve with center of mass being fixed, right? Would rotate about the center of mass, This torque will produce an angular acceleration alpha. Right? The angular acceleration alpha produced is going to be torque divided by I of the system, moment of inertia of the system about the center of mass. I am applying tau equal to I alpha about the center of mass. Torque is what? PE by 2 divided by I of the system. Now, the rod alone about the center of mass, what's the moment of inertia? 1/12 ml squared. Now, the particles, this is L by 2. The moment of inertia of this mass m about this is going to be m into L square by 4. So, 2 into ml squared by 4. Yes or no? L by 2 whole squared. So, that's going to be the angular acceleration at this instant. Yes or no? Torque, which is P by 2 by I of the system. 1/12 ml squared for the rod about the center of mass, and the two particles ml by 2 whole squared plus ml by 2 whole squared, which is 2 into ml by 2 whole squared. Bolo. Nahi kya? Got me now? So that's the angular acceleration at this instant. Obviously, I of the system is remaining the same about the center of mass, but torque is varying because this theta is continuously varying. The system starts to rotate like this. Under the influence of this torque, it has an angular acceleration like this, and therefore it will develop an angular velocity. It will continue because of alpha, it will develop angular velocity in the clockwise sense, right? After a while, it will get into its state of lowest potential energy, right? It will get into its state of lowest potential energy, theta equal to 0, and it would have acquired an angular velocity omega. The rod would have acquired an angular velocity omega. Suppose I want to be able to compute the omega when the rod gets into a stable equilibrium. This is the stable equilibrium state of the rod, right? I want to compute the angular velocity of the rod when it gets into a state of stable equilibrium. That is, theta equal to 0 is a state of stable equilibrium for the dipole, right? Now, so I want to compute omega here, right? I'll apply between these two states conservation of energy. What's the energy here? There is only potential energy because it started from rest, which is like minus P dot E, right? That is, the initial potential energy is what? minus P into E into cos 30 degrees. That's the initial potential energy minus P dot E. What's the initial kinetic energy? 0, because the whole thing started from rest. Right? Now, when it comes to this state, what's the potential energy? Minus PE. Minus PE cos 0. Minus PE cos 0. Minus PE cos theta, right? Minus PE cos 0. So, which is only minus PE. And it will have kinetic energy, which would be half ICM omega squared, which would be half ICM omega squared. So, which would be half of I of the system, same thing. I of the system into about the center of mass into omega squared. So, you can compute omega squared from these considerations. You can compute omega squared from these considerations. Yes or no? Angular velocity of the rod when it gets into stable equilibrium. Okay. Yes, I will. Okay. See, this experiences a force QE to the right. This experiences a force QE to the left. What's the net force on the system? That must be the mass of the system into acceleration of the center of mass. Right? The net forces, one particle that reflects the net force is the center of mass, which means acceleration of the center of mass is 0. And the center of mass was initially at rest, and its acceleration is 0. The center of mass remains at rest. That means this remains a fixed point. So the whole system rotates about this point. The whole system rotates about this point. Yes, please ask. Because this is like a hinge now, because this is not nudging from position. It's like a hinge. So the whole thing will rotate about the center of mass. Clear? Can I wipe this off? Now, see, in a given direction, there is charge distribution. This is my x direction. Suppose charge is distributed as a function of x. Volume charge density. This is volume charge density as a function of x. As a function of x, right? Now, this results in an electric field along the x direction. This results in an electric field along the x direction as a function of x, as a function of x. I want to find a relationship connecting electric field as a function of x and volume charge density as a function of x. What I do is, I take a small cuboid of length dx. I take a small cuboid of length dx whose area of cross section is 1 square unit. Area of cross section, that means along this dx, these areas, these two faces have area 1 square unit. These areas, shaded areas, are perpendicular to the x direction. That means the x axis cuts through these two shaded areas perpendicularly. Right? Now, this is a certain volume. Almost like a point volume, almost like a point volume, almost like a point volume. I mean, this 1 square unit ki jagah, let's say I just call it dA, very small area dA, very small area dA. That will make better sense. So that I could call it a point volume, so that I could call it a point volume. This volume is like dx into dA. This volume is like a dx into dA, almost like a point volume. Yes or no? This is a volume dV, which is like a dx, the length, into area of cross section dA. Yes or no? Now, this is this entire thing as if it's only at x. It's at x. It's almost like at x, right? So the charge inside this volume would be volume charge density rho x into this volume dV. That's a charge, right? Take this volume and rho at x. Rho at x is practically the rho at everywhere in this region, almost. You know what I'm saying? Volume charge density is rho at x in this entire, into the volume dV. That's the charge inside this volume. That's a charge inside this volume, which is rho at x into dV, which is dx into dA. Yes or no? Electric field is perpendicular to these two areas, right? Electric field is perpendicular. Now, there is E at x. This area is at x plus dx. This area is at x. This area is at x, right? And this area is at x plus dx. So the electric field on this area is E at x, whereas electric field in this area is at E at x plus dx. Yes or no? Is at x plus dx. Nahi kya? Now, so there is flux entering, there is flux leaving. There is flux entering, there is flux leaving. Whatever leaves, we choose as positive. Whatever enters, we choose as negative. Net flux leaving. Net flux leaving is this minus this. What leaves minus what enters. What leaves is E at x plus dx into dA is what is leaving. E on this surface into the area of this surface on this of this face, right? Minus what enters is E at x into dA. Yes or no? Which is like E at x plus dx minus E at x into dA. But this is like change in E. Finally minus initially. This is like a change in E. dE. From x to x plus dx, this is like a change in E. dE. Right now? So this is like dE into dA is the next net flux leaving. This is the net flux leaving. And that from Gauss's law must be charge enclosed by epsilon naught. Right? Net flux leaving is dE into dA. That must be net charge enclosed by epsilon naught. This is the charge enclosed. From Gauss's law, net flux leaving would be charge enclosed by epsilon naught. This is the net charge enclosed. By epsilon naught. This is a consequence. This is the net flux leaving, which is like charge enclosed by epsilon naught. Enclosed by epsilon naught in this region. Right? So you can see, you can cancel this. Rho at x therefore would be epsilon naught dE dx. That will give me volume charge density as a function of x. Important result. If E varies in the x direction because of a volume charge distribution, then that volume charge density as a function of x will be given by epsilon naught dE dx. Epsilon naught dE dx would be the volume charge density at various values of x. Right? We use this result commonly. Can I just remove this portion? Suppose I asked you. You can be vocal when I am asking you. Copy. Okay. So suppose this is a direction, r direction. Electric field in this direction varies as, say, 2r squared plus 3r. All right. I want to find volume charge density as a function of r. I want to find volume charge density as a function of r. That's as a function of r, it's going to be epsilon naught dE dr. Epsilon naught dE dr. That's going to give me volume charge density as a function of r. Right? So which is epsilon naught. What is dE dr? 4r plus 3. That will give me volume charge density as a function of r. That will give me volume charge density as a function of r. No, kya? No? No? Didn't understand? This part? Okay. So this was in the x direction. Instead of x direction, I have the r direction. That means along this direction, r varies. R equal to 1, r equal to 2. So rho at r would be epsilon naught dE dr. dE dr is what? 4r plus 3. So rho at r would be epsilon naught 4r plus 3. Use this result directly wherever required. For a one-dimensional electric field, the variation of volume charge density with that direction, in this case we chose that as the x direction. It could be r direction or y direction or something. Then rho at x would be epsilon naught dE dx. Would be rho at x. Clear?